Hi, my name is Skyler, and I'm from the Machine Learning Research team at Apple. I'll be presenting our work REALM, Robust Entropy Adaptive Loss Minimization for Single Sample Test Time Adaptation. This work is in collaboration with my co-authors from Apple, Barry, Fede, Navdeep, and Dan. In short, this work explores the limits of online test time adaptation of image classification models in single sample streaming settings. We identify that seminal prior work fails in this setting, and for methods that do not, we show that these prior works fall under the setting of robust loss minimization. Based on this, we propose a new strategy REALM that achieves a 2% increase in accuracy across multiple corruptions and datasets like CIFAR and ImageNet. More specifically, this paper considers the task of image classification, where a model is trained on a set of labeled images to predict class labels. When evaluated on in-distribution data, models can often produce correct classifications. However, when given corruptions or images out of distribution, such as the variants seen here, like weather and sensor corruptions, the model may not produce the correct classification. In test time adaptation, or TTA for short, the goal is to update the model slightly, denoted by delta here, using the unlabeled test samples. Since we're at evaluation time, this is challenging, as we have no access to source data, no labeled data, no access to change model training, and observed data in a streaming online setting. In this work, we further consider the real-world setting of only seeing a single sample per batch. Now, let's talk about some strategies for TTA. As mentioned previously, we assume that our model F has been pre-trained on some data domain using, for example, a supervised loss objective. At evaluation time, we employ entropy minimization, a method known as TENT. Here, a majority of the model is frozen, and only a small portion of the model, such as the norm layers, are updated according to the batch entropy, which we refer to as a modulation delta. An initial test of ResNet50 on CIFAR-10 shows that entropy minimization does not work in single sample settings. Specifically, we found that adaptation fails due to certain samples, as shown in orange, having high loss on the graph on the left, leading to large gradient updates and quickly overfitting. This leads to always predicting the same label, 6, and after only 1,000 samples, as seen on the graph on the right. This leads to the model failing to adapt to the new distribution and being unable to classify even in-distribution data. Do note that setting a very small learning rate or devising an optimization procedure may work, but this also reduces the amount the model can adapt to the new distribution. This led to prior work named EATA using a piecewise objective that updates only if the entropy is below some threshold. In their work, they proposed two weights, S1, which controls updates to be below a certain pre-specified loss threshold, lambda, and S2, which only updates on samples which make similar predictions. Note that both weights have no gradient update and can be treated as fixed weights, not directly part of the optimization procedure. However, as a result of S1, EATA misses many samples. We can see this in the graphs below for a Gaussian noise corruption on CIFAR-10 and ImageNet. We plot the loss and fixed thresholds and show the number of updates as a function of the number of samples. We see here that many samples are skipped. To expand on this, we extend the EATA 0-1 weighting approach of S1 by first demonstrating that this is a specific case of a weighted entropy objective under the self-paced learning framework, and under certain settings is equivalent to optimizing a robust loss function rho. This means that EATA is a special case of a robust loss minimization problem, similar to methods such as robust regression, which handles outliers in classical regression problems. In our work, we provide a new and more general form for rho, leading to a new optimization procedure. We give the form for rho below and note that we optimize a function of the entropy rather than pure entropy, namely the square root of the entropy, as this corresponds to a regularized weighted entropy optimization. We also derive the new form in terms of a learnable weighting alpha and learnable threshold lambda. The form is not that important, but to understand why this parametrization is beneficial, let's examine the graphs below for what rho looks like in the squared loss and draw a comparison to prior objectives. When alpha equals 2, this corresponds to no weight, and the derivative, which is tied to the model update, will change parameters drastically, as shown in blue. Equivalently, this is traditional entropy minimization. In contrast, a smooth approximation for the 0,1 weight corresponds to alpha equals 0, which yields little to no gradient update on samples with high loss. This is similar to what is done in EATA and is shown in dark blue. Using our robust loss allows us to learn how much penalization to apply through alpha and the proper threshold lambda to set per dataset, giving more updates even for high loss samples. A broad overview comparing realm with prior work shows that in addition to optimizing new model parameters, theta, we also learned the weight alpha for penalization and threshold lambda terms to more flexibly adapt to the new data distribution according to the robust loss rho. Empirically, we find that realm achieves about 2% better performance on CIFAR-10 across several corruptions on the common corruptions benchmark, and roughly 1.5% on average on ImageNet along the same common corruptions. We found that realm performs the best on average across architectures. However, results varied across competing methods even though the model architectures have roughly the same number of parameters. Finally, we found that realm improves on other domains as well, including style differences from ImageNet renditions and natural adversarial examples from ImageNet adversarial benchmarks. In summary, we showed that online TTA methods fail on single sample streaming settings. We demonstrate that prior work falls under the setting of robust loss minimization and show better performance by designing a better robust loss for entropy minimization TTA. Thank you for listening.